Hello, I would like to spend a little bit of time with you today talking about speeding up and slowing down. Speeding up means that the magnitude of my velocity is going toward infinity or away from zero. And slowing down means that the magnitude of my velocity is going toward zero. These two conditions here can be understood in terms of the SIGN sign of the velocity and the acceleration function. So let's work on this particular example that I have written down here that I just kind of made up off the top of my head. Let's try to find out for a particle undergoing linear motion with a position function s of t, when is the particle speeding up and slowing down? Okay. To remind you about what we're going to do in terms of how to know the answer to this question in terms of the velocity and acceleration functions, speeding up means that the velocity and the acceleration have the same sign. And the slowing down phenomenon is that the velocity and the acceleration have different sign. So our method is going to be to compute the velocity and acceleration functions and plot them, and then see where they have the same or different signs. Okay. Let's compute the velocity function v of t. That's equal to s prime of t, because this is the position. So we'll take the first derivative, the first time derivative of this expression right here. 3t squared minus 4t plus 3. And the acceleration, a of t, is equal to v prime of t, or the second derivative of the position function, which is going to be 6t minus 4. Okay. So we've got an upward opening parabola and an upward pointing line. So we want to know where these two things are positive or negative. And we could do this either by plotting them or by figuring out their zeros. So I think I'd like to do that by well, let's do the zeros method first. So let's figure out when the velocity is 0 and when the acceleration is 0, and then use those to plot. Okay, so I know that the velocity is going to be a parabola that looks like that, and the acceleration is going to be a line that looks like that. And we just got to figure out where do those things cross the horizontal axis. Where do they have roots? Okay, so we're going to set them equal to 0 and solve. Okay, so a of t equals 0 means that 6t minus 4 equals 0. And we can add 4 to both sides, and I'll have 4 equals 6t. So then divide by 6 on both sides, and 2/3 equals t. So this value right here is 2/3. Okay, so I know that the particle is undergoing negative acceleration until time 2/3, and is undergoing positive acceleration after 2/3. I happen to know that since this line is the derivative of this parabola, that this vertex is also at 2/3. So it's vertically aligned, and that's fortuitous for us. So this time here is that time there, that halfway point. So we just need to figure out where these 2 points are right here, and then we'll kind of be ready to go. So let's play that same game, set it equal to 0 and solve with the velocity function to figure out what its 2 roots are. Okay, so I want to know where v of t is 0, or when, possibly. And that's when 3t squared minus 4t plus 3 equals 0. I'm just going to erase those because I don't think those are particularly helping me. I just wanted to write those down. If I had infinite board space, I would totally keep them. You know what I think I'm going to do is I think I'm going to use the quadratic formula on this because I don't know how to factor it off hand, because my middle term, if I divide by 3, I'm going to end up having a 4/3 here. I think this thing is irrational, so I don't think I can do that by factoring. Let's see here. So I need the quadratic formula. It's minus b plus or minus the square root of b squared minus 4ac all over 2a. That's a, b, and c. Okay, so that's 4, because minus 4, plus or minus the square root of 16, minus 4 squared is 16, minus 4 times a times c. Did I choose bad numbers? I'm going to have to start this video over again. Yeah, I did. Well, son of a gun. We're gonna carry it to conclusion anyways, and then we'll do another problem. That's fine. All over 2a, so that's all over 6, because the leading coefficient is a is 3. 2 times 3 is 6. Okay, 4 times 3 is 12. 3 times 12 is 36. 16 minus 36 is negative 20. Which means that we have a complex conjugate pair of imaginary or complex numbers here, which means that the drawing that I made on my plot over here is slightly incorrect. I do have a parabola, my friends. I do have a parabola, and it's still its vertex is still right above 2/3, but it never crosses the horizontal axis. So this particle is always moving forwards. Oh no, this is still going to work out just fine. This problem is going to be just fine. Yeah. Okay. Okay. So, this parabola given by v of t has no real roots. And so what I'm going to do is I'm going to then consider that v of t is always positive. Yeah. Okay. So we know that v of t is always bigger than 0. And I know that as far as my line goes, a of t changes sign at 2/3. Over here it's negative, and over here it's positive. V of t is always positive. So where are they of the same sign, and where are they of different sign? Okay, that indicates speeding up, slowing down. Speeding up is where v of t and a of t have the same sign. So they have the same sign over here, so the right of 2/3. So the particle is speeding up from 2/3 to infinity, and it's slowing down from 0 to 2/3, except I want to include the 0, the time equals 0, because my experiment starts at time t equals 0, and it's moving at that time. So it's definitely slowing down at time equals 0. So I'm going to include that time with the square brace. Okay. So I feel like the tactic here was I wanted to come up with this line, and I'm gonna partition the line according to the zeros of my velocity and acceleration function, and then I'm going to check and see where they are of the same sign and where they're of the different sign. And they're of opposite sign here, to the left of 2/3, so it's slowing down. And to the right, they're of the same sign. It's both pluses. If they were both minuses, it would still be speeding up from 2/3 to infinity in this particular problem. So I feel like that's a pretty strong tactic for dealing with this, is constructing these two little lines with the SIG and signs of the two derivatives on it, and just figuring out where do they match and where are they different. I'm going to go ahead and repeat this with slightly different numbers at this point. So if you got what you needed out of this video, then by all means stop. But if you want me to do this with different numbers, then by all means keep watching. Okay. Because I wanted the parabola to actually cross the t-axis, and my randomly made up numbers didn't make that happen. So how do I change this problem so that it actually crosses the axis? Well, I think I can erase that like that. I don't need that. So let's just twiddle a coefficient. The problem was that minus 4AC was too big in magnitude. So if I make B bigger, if I go to so this produced 36. And so if I make this number be a 7, that should be sufficient. Because then I'll have 49. Okay. So we still want to find out where do V of t and A of t have the same sign and different sign. I'm going to take the same approach to that. I'm going to differentiate it. I'm going to differentiate it again. I'm going to find the zeros. And then I'm going to do this analysis in terms of SIG and signs of these two functions to break up the intervals. Okay, so V of t is 3t squared minus 14. Oh, yeah, this is totally going to work. Minus 14t plus 3. And A of t then is 6t minus 14. It's still a line. The acceleration function is still a line that points up like that. And it's going to 14/6 cross the x-axis. And 14/6 is the same as 7/3. So we just need to figure out, we're going to have a parabola that's going to open upward like that. It's going to be positive and then negative and then positive. So let's just figure out where those 2 points are. And so I'm going to do that by doing the quadratic equation on the velocity function to find those 2 roots. So I want to know where 0 equals 3t squared minus 14t plus 3. Negative b plus or minus the square root of b squared is 14 squared minus 4ac, 4 times 9, all over 6. So here's that 14/6 again, right here. And then we're plus and minusing. So this right here, the discriminant, is the distance away from the center point that those two roots are. 14 squared is, let's see here, do I know my numbers? 13 squared is 169. 14 squared, 15 is 225. 14 squared, 14 times 14 is 140 plus 4 times 14, because that's 10 times 14. 4 times 14 is 2 times 28, which is 56. 4 times 14, 28, 56. Okay, so it's 196. As 14 plus or minus the square root of 196 minus 36 all over 6 as 7/3 plus or minus the square root of 160 over the square root of 36. I'm trying to think about how I want to simplify this thing, and I think it's useful that you experience my thought process as far as I go. So I can square this 6 and put it underneath the square root like that, and then I can go like that, and then I have the square root like that, and then I can simplify 160 over 36. So let's do that. Let's say take out 2. I'm going to have 18. In the numerator, I have 80. And then let's do a 2 again. I'm going to have 9 and 40. How about I split that square root again, and then I replace my square root of 9 with 3? Then I could rewrite my 40 as 4 times 10. And then let's split that square root across those, and it's going to turn into 2 root 10. Ooh, that is so nice. Okay. So those are these two values here. I better transcribe that over here. So we have 7/3 plus or minus 2/3 of the square root of 10. That's a 10. Okay, that was all side work, scratch work, if you will. And now I'm going to use that to construct my little number lines that I'm going to label with pluses and minuses, and ultimately apply this have the same sign, have different sign thing in order to do the analysis for speeding up, slowing down. Okay, so V is here. This is at 7/3 minus 2/3 root 10, and this is 7/3 plus 2/3 of root 10. And look, it's an upward pointing parabola, so it goes like this. So the parabola was positive, and then it's negative, and then it's positive, right? Because the parabola is positive, and then it's negative, and then it's positive. Positive, negative, positive. I've got my A of t number line, which splits right there at the number 7/3. And it's A of t is negative, and then it's positive, negative, positive. So there are some intervals here, and we need to like break them up. So how about I put a third number line here with 3 tick marks. Minus infinity is all the way over there, but my experiment starts at time equals 0. Positive infinity is all the way over there. This is 7/3. This is 7/3 plus. I think I'm going to write with a finer. We know what those numbers are. 7/3 plus 2/3 of root 10, 7/3 minus 2/3 of root 10. Okay, the velocity is going to be on top. It's positive, it's negative, it's negative, it's positive. And the acceleration, so those are the V's, acceleration is on the bottom. It's minus, it's minus, it's plus, it's plus. Right? So I took the accelerations. Maybe I'll put these ones below. There we go. So I combined these two. So I can tell just by looking at these SIGN signs of velocity and acceleration that it's the particle is speeding up right here and it's speeding up right here because the signs match at those two places. So up. And then it's slowing down at the other two intervals because they're of opposite SIGN sign. So here it's down, slowing down, and here it's slowing down. So I'll write one of the sets of intervals. How about I do the slowing down one? So where is it speeding up or slowing down? It's slowing down where V of t and A of t have different sign, that interval to that interval. It's slowing down from 0, 7/3 minus 2/3 of root 10 paren. When it is locally standing still and it's doing nothing, it's neither speeding up nor slowing down at these transition points. And then again, for this interval right here, so combined with 7/3 to 7/3 plus 2/3 of root 10. And then it's speeding up in that interval and that interval, right? So let's kind of bring this back full circle to the graphs of this thing. So so this is the velocity curve. Here, it's the particle is moving forward because the velocity is positive, so it's moving forward. But its velocity is going towards 0 until it stops here. Here the particle stops at these two places, right here and right here. The particle stops at those two places. So it has to slow down in order to stop. It slows down in order to stop. And then it speeds up as it moves away. And then it's still moving forward, but it's coming to a stop again. And it slows down during this window right here. And then it speeds up, and its velocity is going towards infinity. And it's going to speed up forever, presumably until it escapes the universe or something. So hopefully you find that technique useful in analyzing speeding up, slowing down for motions, bodies along lines, what we call linear motion. So I think I'll stop there and say thank you very much for your attention, and I hope you have a lovely day. Bye.